welcome you to Maniac's talks. My name is Charles Gatebe, you don't know me. Now today, we very fortunate. Fortunate because this year, as you know, we've been celebrating the Hubble Space Telescope, 25 years of discovery. And one of the pillars of servicing Hubble is with us today, Frank Cepollina, who not only has been here some of the longest period, 52 years, I think. And so we are very lucky, and I'm so privileged to have him here. So please, let's give him a round of applause to welcome the man. And to introduce Frank Cepollina is Jim Jelatic. Jim Jelatic is the Deputy Project Manager for Hubble Space Telescope. Please help me welcome Jim Jelatic.
Okay, so just some of the formal background of Cepi, just so you know, he was born in Clear Valley, California. He was raised on a farm. I'm anxious to see a picture of Cepi milking a cow someday. But he went on to University of Santa Clara, where he got a bachelor's degree in mechanical engineering, graduated in 1959. He worked in the defense area for a little while, and then in 1963 he came to Goddard, where he worked building satellites. Eventually, they gave him the responsibility for those who remember the multi-mission modular spacecraft. That was kind of it had many roles, but one of the main ones that I was related to from the work that I did when I first came to Goddard was it was kind of a standard spacecraft that you could use from mission to mission, and that so you could standardize various things, whether it be ground system software or hardware for the spacecraft, etc. So he was responsible for that in the 1970s, along with he actually supported some of the Hubble work with building Hubble in terms of helping with understand the module designs for instruments and things of that nature. In 1984, there was the Solar Max mission, which was up in space and had a problem, and he was called upon to figure out if we could and how we could fix it on orbit. So that was kind of like really, although there was some work done by astronauts obviously in space before that, but that was really the first of the satellite servicing. From there, he would go on to be in charge of all the Hubble servicing and development of all the replacement hardware for Hubble, the new instruments, and things of that nature. And obviously, the success of Hubble is greatly he's greatly responsible for that in terms of the technologies and things of that nature. After Hubble was over, Cepi would become head of the now NASA Satellite Service and Capabilities Office, where he's working on developing the technologies and capabilities that you need for whatever servicing is needed by the agency. So that's kind of the formal side of Cepi, and so that you kind of know, the background. But then there's the other side of Cepi, and for those of us who have known him and worked with him for years, he's an interesting guy. So the first thing I'm going to tell you is that he is the definition of a mover and shaker. Okay, period. There's nobody that I can think of that makes things happen more than Cepi does. During the Hubble mission, one of the reasons we're so successful is because every time we put on a new generation of instruments, they were better than the one before. And some of that is due to Cepi's refusal to accept that we can't make things better and even more better. And so, some of the examples of that are the CCDs that were produced, the advancement in the CCDs. It was really him that was the force behind a lot of that for those particular instruments. And now they're actually been used in terms of tech transfer for other things, such as helping uncover breast cancer, and also, for those who know Dead Sea Scrolls, some of the infrared capabilities from those sensors were later used to read what we, at that time, was thought to be the unreadable Dead Sea Scrolls because of their deterioration, but put under infrared light and an infrared camera with our detectors on it, etc., you could actually see some of that text. So he's pushed technology beyond belief. He built up the whole concept of servicing. I mean, if you take a look at the Hubble missions and all the infrastructure that had to exist, from the carriers to the tools and crew aids that were developed for the instruments, and et cetera. It's really incredible the amount of technology and amount of work that had to be there to make that happen. And you know, he makes things happen. So if you take a look at right now his current job, realize that there was no announcement of opportunity for satellite servicing capability. That he just simply submitted a proposal, and then he won, and now he has a whole office and staff and budget to do that. He has to convince a lot of powers that be that this is the thing that NASA needs to have for the future, and then he needs to convince them that the amount of budget that's needed and the technologies that are needed and where we can apply it and what experiments we can do on orbit to apply it and things like that. And that takes an awful lot of politicking for all kinds of things at the appropriate levels. So in a nutshell, there's those people who follow. Right? And followers are very, very important, okay? Because work doesn't get done without them. There's those people who lead, okay? And I don't put Cepi necessarily in that category of those people who lead, because I put him in the category of there's those people who set the standards for leading, and that's Cepi. So he's going to tell you a lot about the capabilities that really he's been responsible for that got him into the National Inventors Hall of Fame, along with Thomas Edison and that, and it's well deserved. And what he's doing here at NASA and how he made that happen. So please welcome Frank Cepollina.
Okay, well, I thank you all for coming. I recognize a lot of you. A lot of times it's because I have lunch with you in the cafeteria. And others it's because we have battles together. And Henning Leinecker and Lee Niemeyer, I see a lot of friends, Christy Hansen. I remember one time where I made Christy come into tears, right? But it's all in the interest of getting a job done and picking the best of the best people, and having the best of the best people engaged in working on something you believe in. And I see some of our future astronomers back here as well. And so I'll be talking about entrepreneurship. I'll be talking about applying technologies to practical applications, applying other technologies that we've never even used before. By the way, I'm open for questions, so just pop your hand up, just yell at me anyway. Stop me and we'll try to answer your question. One thing that needs to be said, I've been here a lot of years. I apologize about that, because I've always threatened, this is my last year, this is my last month. I say that almost every day I'm driving in. I live in Virginia, and I've been living there for 50 years, so you can imagine what I go through to go back and forth to work. But the most important part about all of this is working with you kids. And pardon my expression, but I call everybody kids now, okay? Because I think that it's sort of like a family. It is a family. It is a family. We do things together, and we argue things, we fight things, we fight about things, but in the end, we do the best job we can do, and we do some great stuff. And it's the great stuff that I want to go on and talk about. But one of the most important parts is you got to understand me and why we're even doing this stuff of repair and maintenance of satellites in orbit. First, most important part is I grew up in the Depression. Now realize most of you weren't born in the era of the Depression, right? Anybody born in 1935, 36, 37? No, nobody here, right? Most of you were born after World War II, right? Well, I grew up through World War II. But I also grew up on a farm and on the Depression. The one thing you never did, you never threw anything away on a farm, and you fixed everything that broke. The best you could, but you fixed it. So maybe that's culture is grown up with me. I think so. I think how I got into this, I see Komar back there. He grew up in the Depression. No, Komar? No. I'm not that old, Seth. Nuts. Okay. All right. So at any rate, so that's where all of this is coming from. And when I got to NASA, the first thing that happened was I was struck by the fact there was only 6 buildings And I think there's 36 now or something like that. But it was only 6 when I first got here. And they had just announced the Apollo program a few months before I got here. And I said, oh, I'm getting here too late. The challenge is all over. And that was like in March of '63. So I found out in a hurry that 1/3 of all the spacecrafts between 1960 and 1970 that we were designing and building and launching, 1/3 of them, 1/3, and they weren't cheap even in those days. They were $100 million, $200 million, $50 billion programs. 1/3 of them failed short of 90 days on orbit, if they even got to orbit. Some of them didn't even get to orbit. Some of them, the shrouds wouldn't come off, and the spacecrafts went back into the drink. So there was a great challenge in 1970, started by George Low, the then deputy administrator, that says, NASA, Goddard, you guys build most of the spacecrafts, you got to find a way to solve your problems. We got to make those things last longer, get in orbit, get more scientific return from them. So he challenged a group of people at Goddard, and I got on that team, so to speak, that ad hoc team, and we put together a concept that would take advantage of the two-way capability of the shuttle, which was being thought of at the time as a new concept for transportation to orbit. And if in the event your satellite got to orbit and it didn't work, guess what? You could close the doors, bring it back inside, bring it home. And we'd fix it and launch it again. That was the kind of one of the potential economic benefits of having two-way capability to space. And I'll show you how at times that panned out pretty well. And it certainly panned out for Hubble. Now, in doing that, this ad hoc team, and I don't know if any of you remember John Mangus. John Mangus? Oh, there you go. Joe Purcell. Some of us old-timers. Nancy Roman, head of astronomy at NASA headquarters and so on. We developed a concept for a modular, repairable, shuttle-launchable telescope. And we called it the Large Space Telescope. And it was 3 meters in diameter. Now, I'm going to start off this way because I want to get a message across. Everybody says today, when I come to me about, hey, we want to get a new program started. And I turn around and I look at them, I says, well, what do you do to get it started? Oh, we got to get this paper. We've got to get these 1.5 year proposals. Then we got to get in line. And then we got to go to headquarters with our proposals. And then we got to hope that we beat everybody else out. Well, that's 3 to 5 years. I said, this is crazy. We can't do it that way. So what I'm trying to tell you is we didn't have a dime. We had a paper concept that we put on drawings, hand drawings, not computer drawings. They didn't have computers in those days. And guess what? We didn't have a dime to do it, but lo and behold, one thing we had was desire. Desire. So all of you, and I know most, how many here are scientists? Oh, okay, not as many as I thought. Well, how many of you want to fly your instruments to orbit? How many of you are building your instruments now? There's a lot fewer hands. Why aren't you building it? Well, because you have no money to get started, right? Yeah. You have nobody to get you. You don't need any of that. What you've got to do is have ingenuity. You've got to go find the resources. Right, George? You and I know that. You've got to go find the resources to do the right thing. And what we did in 1970 and 71, we went to guess what? We went to the new business guide put out by the GSA that said, here's all the property around the entire government system that any other government agency can have. And we saw on that list all of the titanium for the SST. Does anyone remember the supersonic transport? Yeah. Okay, and you know the building you all are sitting in right now, you know what that was? That was a warehouse. It was an empty field of grass, and 600,000 pounds of SST titanium was delivered here at no cost to the government other than an agreement that we would never sell it, number one. And number two is that we would only pay for transportation for titanium that came from Chicago to God, not from Seattle or not from other companies around, but only from, and there was a big explanation for that.
But at any rate, the point is, this center started off in 1971 with 600,000 pounds of titanium, all dimensions, all stock, all plate, all GSA available as a part of the transfer. Now, you know, if you go to those schedules today, you know what you're going to find? You're going to find all kinds of material. You're going to find enough material to build 2 telescopes. Now, they may not all be aluminum, they may not all be titanium, but there's a lot of excess material that's available to government agencies floating around those GSA advertisement catalogs. And that's what you need to do. And what we did with that 600,000 pounds of titanium was we gave most of it to other flight projects that wanted to get started. But we used quite a bit ourselves, 60,000 pounds. We built a 3-meter diameter, 35-foot primary mirror telescope structure, all out of titanium. And guess where we did it? Where did we go? We went to the shop. We went to Building 5, right? That's how things get started. And we taught Lee Meyer's predecessor into helping us develop this new technology for welding titanium. Remember, this is 1967, 71, 72 time. And they built these systems in the house, all out of titanium. Now, once in a while, we had to cheat, and we went to, with all the raw stock of titanium, we went to a company called Titanium Metal Climax. They got a different name today. And they forged us a 3-meter in diameter primary mirror support structure for this design. We built the design up, all in an engineering sense. Yes, we did our rudimentary stress analysis, make sure we didn't kill anybody with all the GSE. The Canadians saw what we were doing. The Canadian government saw what we were doing, and we convinced them to come and build for us this blue structure, which we call the berthing structure and change-out structure, that allowed this modular telescope, which was called Large Space Telescope, to be changed out with a push of a button from inside the shuttle cab, not even any EVA. Now that was a mistake, because as you'll find out, there's another part of this agency, another department that would like to send astronauts into space to do important things. Well, I'll talk about that again. Everybody thought we were nuts, demonstrating that we could take a
large space telescope designed to fit inside the shuttle orbiter and service it by the push of a button. And that's exactly what we demonstrated in 1G without any money, with the help of North American Rocketdyne, which happened at Downey, California, to have this plywood mock-up, very early concept, plywood mock-up of the shuttle. Why am I telling you this? Because that's the spirit of entrepreneurship. If you kids want to fly your scientific instruments, if you want to collect great new breakthrough scientific data, you've got to apply that entrepreneurship. You've got to apply that. You cannot depend on the bureaucracy. It'll kill you. You'll be an old man or an old woman by the time you're ready to fly an instrument. You don't want that. You want to apply entrepreneurship. The greatest degree of thinking is how you're going to work around the problem of not having any money. And I remember once somebody coming to me says, I got a photo engraver. He'll engrave plates. Can you build us a printing press? Well, you know, there are limits, right? But I got to admit, I thought about it for a second or two. Yeah. All right. So from that, we lost the Large Space Telescope program. Goddard had too much work. Marshall didn't have enough. So they made in 1974 a fateful decision that says, we're going to give the shuttle program, the Hubble program, to Marshall Space Flight Center, but we're going to have Goddard keep the instruments, and we're going to keep the modularity and the serviceability concept so that we can take advantage of the shuttle at a later time to repair and maintain Hubble. Very insightful decision. Yeah, we really felt crushed, but it was a downstream, very important decision from the good of the agency, and I'll explain that in just a little bit. But the most important part, they came back and they said, but guess what? We don't want to start Hubble program going without a pathfinder. So we're going to give you a mission called Solar Max to build in a modular sense so that it can take advantage of modularity, lower cost approach for integration and test, that's our other term for modularity, and can be serviced in case it had to be serviced by the orbiter. But we don't want you to spend any money to incorporate serviceability, and we don't want you to talk about it. But you do it. And so we put a project plan that basically said that very thing. And we went off and we built Solar Max, and we launched it in 1980 on a conventional launch vehicle, but it could have been launched with the shuttle just as well, but the shuttle wasn't ready. We went. We got in orbit, we went 3 years, and we had to repair it. And by virtue of the fact that everybody remembered that it was designed to be serviced by the shuttle, they said, guess what? You guys go up, don't spend any money, and we will get the manned space program to support you. And the manned space program stood up, and they built some of the interfacing hardware and started off that way. And we got the program going. Pretty soon, SMD, remember that directorate that we all work for now and then? I notice I say now and then. But they put up the money for the replacement hardware, which was a new electronics box for the scientific instrument, and prepared the funding in our bodies, our people here at the center, to prepare to do the servicing mission. We did it, and right behind them, within 6 months, all these companies lined themselves up to, guess what? Do servicing missions for their satellites that had failed to go to orbit or failed to go to the destination they wanted their satellites to go to. So it was Westar, Palapa, Intelsat 6, SYNCOM 4, and I think I left one out. But anyhow, all those missions were done. But the interesting one, and those were important because they were either rescued, repaired, replaced, hardware was replaced. 2 of them were brought back to the ground, refurbished, and then taken back to orbit and put in operation. But the most important one was one that was worth about $500 million. Wes and I were on that program, Wes Owsley. And that was called Compton Grow. Does anybody remember Compton Grow? Yes, right, we played a role in that. But you realize that when Compton Grow was launched inside the shuttle and taken out of the cargo bay, it was a total loss because they could not deploy the high-gain antenna. Does anybody remember that? No, they never talk about our failures, right? Never, right? And they don't even talk about the successes. So what did they do? The astronauts, pretty clever, they hadn't released Compton Grow because they hadn't deployed that antenna. It would not deploy. They brought it back into the cargo bay. They sent 2 astronauts out with the same kind of tools we used on Solar Max, disengaged the hinge of the antenna, saw that MLI was caught in a hinge, removed the MLI, reinstalled the antenna, lifted it back out, deployed the antenna, and guess what? You had 11.5 years of operational success with Compton Grow and data. You had the high-gain data antenna deployed and operating successfully. So there's a fundamental message. So one of the concepts, 2 of the concepts, repair and maintenance, take care of your failures when they get to orbit by repairing on the site, or if they were not repairable, bring them back to the ground and fix them and relaunch them. 2 very important principles. So I go through all of that, and of course, history would have it, guess what failed thereafter? Hubble. It wasn't even a failure, it was just a mistake. And there were about 5 mistakes on Hubble, not just one. It wasn't just the primary mirror. Primary mirror, I thought, was a work of art. It was only wrong by half the diameter of a human hair, right? Half a 50,000th of an inch. That's pretty small, but that's how much the polishing error was, and it made a big optical difference in the telescope. So I'll talk to that in a second. But there were these 5 other things. We had a solar array that you can see up there that had a 60-degree bend on it. That solar array kept wiggling and taking the spacecraft off target every orbit, every day-night cycle. That was just one. Then there was gyros and so on. And Jim Gillette knows the sad story, but we tackled every one of them. We tackled every one of them and we fixed them. The biggest fix, of course, scientifically, was to correct the optics. And everybody says, fantastic. You fixed a $1.6 billion, $1.9 billion telescope and you got it back on. That's great. No. That had nothing. That was not the essence of the investment. George knows what I'm talking about. The essence of the investment was the spin-offs. What happened? What happened as a result of diving in and spending another $500 million to come up with all these optical fixes and the solar array fixes and so on? What was the real essence of it? And that's what you have to focus on, because you're not here just for astronomy. You're not here just for earth sciences. You're here to better your lives and the lives of your children and your grandchildren. You're here for the advancement of humanity. That's why we do these things. And that's what I want to inspire you to remember. We do these things not because of the near-term goal. We do these things because besides the near-term goal, there's the wider-term goal. And it's that wider-term goal I want to show you a little bit about, because I'm going to challenge you to move forward. I'm not going to let you sit on your laurel and go for another 6 years before you ever win an instrument program. We got to do things better than that. We got to do things sharper than that. Now, that's CoStar. That's the instrument that fixed Hubble. And we took an old instrument out and put that instrument in. But the essence of that instrument were these 6 arms. It collected the light, the obscured light from the poorly focused primary mirror, corrected it by having correction, equal and opposite prescriptions, so that we were able to straighten out the obscuration that was the result of the primary mirror being depolished, not polished enough. And we put those lenses in. Now those lenses were the size of a 25-cent piece, the size of a nickel, and the size of a dime. And they were all, every one of them, were aspheric. To correct for the aspheric. Now that means they're not a pure sphere, they're a ripple sphere. And now you try to measure on a piece of optics that small, you try to measure the ripple effects of a sphere that's significantly less, an order of magnitude less, than 1/50th of a millimeter. That is huge. And the technique by which we did that was a technique that made your lives and your grandchildren's lives a hell of a lot easier, and my life, although I hate to admit it, a heck of a lot easier today than it was in the 1990s. And let me show you what that was. Oh, I can't. I'm going to come back to it. I'm going to show you what it is. It'll hold you in suspense. In addition, we had to fix all these other things that were wrong. And the astronauts have several limitations. The first important limitation is they have to eat. And that's terrible. That slows you down, right? Then they have to sleep. And that could be even more frustrating because they don't like to sleep in space. They bounce around and they got to strap their, it's a pain in the neck. But most importantly, they only have 5.5 hours outside in EVA in their spacesuits before they start to run out of oxygen. Now they put some margin and contingency, and we have had times on Hubble where we've gone 8 hours in EVA, but nonetheless they have these human limitations. So in order to get around these human limitations, we gave them power tools. You remember that? It's the same thing that carpenters use on the ground. Power saws, power screwdrivers, power wrenches, power hammers. We gave them those kinds of materials. And what you see there is an astronaut with one of the principal tools strapped on to his suit, but he had all kinds of tools. And they're using these tools on station today and similar design. So it started a tool manufacturing concept. And of course, as things go, competition goes, in wonderful directions, right? Do the recipients of those tools come back to us today and ask us for more? Very rarely. They go out and they go and buy them out in private industry, and they say, here's a tool that NASA developed. Can you build me a replica? And they do, and they get proposals, and we pay the price as taxpayers. So look, the most important thing I got to say about CoStar wasn't the fact it fixed Hubble. The most important thing I have to say about CoStar is it fixed us. You know why it fixed us? Because the key in being able to measure the optical asphyguration of those little dime and quarter-sized spheres depended on holographic measurements. Holography was key. And there was one group in the United States that recognized that, and that was a company, a quasi-commercial and government-owned company called Cepollina. And they realized right off the bat that in order to improve the density of chip manufacturing, in other words, get more transistors on the head of a pin, they needed to tackle the holographic question, or the measurement question of getting sharper and finer lines, and I've got to use a term here, fringe pattern lines on optics so they can more accurately measure the quality of these little tiny mirrors that they use in their photolithography equipment. Now, in those days, the mirrors were like 2 inches in diameter. Today, they're like 6 inches in diameter. But the principle of holographic technology and measurements was pushed very strongly by our ability to try to polish and measure these aspherical tiny optics that we put in that CoStar instrument. And from that capability, tremendous gains were made. And I just put this other photograph up as a comparison. In the 70s, when we flew Apollo, we had a processor that did the orbital mechanics processing on the Apollo vehicle. The equivalent of today's i6 phones, what I got yesterday, as a matter of fact, is 260,000 of those Apollo computers are now embedded in my phone. And over 600,000 memory elements are in the phone. There's enough memory elements in this i6 phone for 7 chips to encompass the entire library of 1 year's worth of data of Hubble. That's immense. Now, how did you do that? We did that by photolithography and being able to take and advance the chip manufacturing capability so you can put many, 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 many more transistors on the head of a pin. So, and there are numbers on some of these charts that show the correlation, but it's 1/1000th of what it once was, which is a huge gain in terms of density packing and being able to build microchips. So we talked about one of the benefits that technology push in the scientific arena brings to the public. Are there any questions on that? Does anybody doubt it? 1266, call me if you don't want to raise your hand in public. I'll argue with you on the phone, or come and see me. I'm in building 12. But my point is push, 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 push. How many of you here, another push, how many, and this one goes to Bruce Woodgate, and there's a few of us scientists that were here then, weren't they? Raise your hand? Yes, right, there's 2 of them. Right, I'm not a scientist. Bruce Woodgate. We were developing an instrument called the STIS, Space Telescope Imaging Spectrograph, and he needed a detector that would be capable of imaging very faint stars. So he had the vision. He was raised in England, right? Which I always excuse him, but I said there was something common about him. He was in England and I was in California, right? I grew up on the farm. I don't know where he grew up, but we always kidded each other about that because he had the vision to find out what the medical industry was doing. What were the medical industries doing about building CCDs that could detect cancer, were powerful enough to pick up radiation under your skin and reflect the radiation differences or the temperature differences in effect between growths under the skin and the skin temperature itself. And he discovered that at University of Kentucky, under the auspices of the Kentucky University Medical Association, was developing a CCD detector that was trying to do that sort of thing, because they had in mind the development of an instrument, I'll talk about the instrument in a second, that would penetrate that. So in 1983 or 4, with Bruce Woodgate under our tutelage, we were developing the STIS instrument for a 1997 launch, second launch. And guess what? So we went there. They sent us to Oregon to their commercial vendor, which was a foundry called Site. And that foundry in Beaverton, under the contract of Bruce Woodgate and the project, helped make the tremendous push we made in developing these STIS CCDs. And yes, these CCDs were tremendously powerful. So powerful that we burned the first dozen out when we took them out at night in an Earth environment and looked up at the stars to try to calibrate them, right? We burned them out. The stars were too bright. So we learned something right away. We learned to use filters right away. Okay, but the point I'm getting at was, in the end, we launched, I think it was like February or March, we launched in 1997, we launched the STIS instrument to orbit with this detector technology in there. Before we lifted off the ground, there were over 1,000 of these machines in doctors' offices and hospitals all over the world, all over the United States, To do what? Breast mammography. And 5 years later, there were over 10,000 of these machines. And a whole industry had developed in CCD breast mammography to detect cancer. And they work. And they had a tremendous impact in reducing pain, reducing necessity for doing surgery, scarring, healing, amount of hospital stay you needed. You didn't need any hospital stay for this. Within 3 hours, you knew whether there was a problem or not. The doctor knew. He could put you on this machine. He could see right through. He could see where there were suspicious lumps. And he'd say, I think you got one. He'd do a biopsy right on the spot. He'd pull out the tissue. And he'd say, okay, we got it. You just got a little pinprick. And it was done. And you knew within a matter of days whether there was important enough to go back or if everything was okay. Thousands, I think there were 10,000 of these machines within 2 to 5 years after STIS was in orbit. That's what I'm telling you about. It's not just us. It's not just our near-term science discoveries. It's the human implication we make by pushing these technologies. Yeah, I'm not done yet. You think you're done. You're actually good here for another couple hours, right? But you can leave if you like. All right, so that's one. That's two. There's others. There's others, but I tried to bring them ones that are more important out because I think they have more implications for us and our children and our grandchildren and their children, whatever. There's one called robotics, right? Now, how many of you realize today we do robotic surgery? Oh, quite a few. Oh, well, this is old hat then. Sorry about that. But I'll talk to it anyhow. Is that okay? All right, now I'll talk to a patient. All right, but we developed all these tools. These tools had microprocessors in them. They weren't just squeeze a trigger and run. They all were calibrated. You could do numbers of turns. You could do torque. You could do force. All different types of sophisticated microprocessor technology were embedded in these kind of tools, including the RMS, the arm that's used to capture the spacecrafts that need repair. And guess what? Along with those robotic developments came two companies. One is intuitive surgical. Anybody ever hear of intuitive surgical? Okay, she does, because she worked for me. Marion does. But intuitive surgical builds a surgical instrument called a Da Vinci machine. Does anybody hear Da Vinci? Yes, the Da Vinci robot. Okay? And another company in Canada, which participated with the Canadian arm, robotic arm development, called NeuroCam? NeuroArm? Okay. Developed the second system. And they're both today competitive robotic surgical systems. And they do some interesting things. And this is a picture. The patient is on the bed, or should be on the bed. I guess it's time to go AWOL. But the patient's on the bed. That's the surgeon over here. This is the surgeon. And he's operating through the screen. He's operating through a microprocessor, and he's got the scalpel technology and tactility sensors on his fingers. And he's moving that scalpel and sees what he's doing in that patient's brain by looking at the screen. That's kind of an ironic thing. But now, it's tremendously powerful. One of the reasons why it's so powerful, it can do neurosurgery. Has anybody here had relatives or friends or whatever that suffered from brain tumors? 1, 2. All right. Now, you know today the brain tumors are a lot easier to detect because they've got a new instrument called what? MRI, right? MRIs. You can see tumors in the brain today that you could never see 30, 40 years ago, 20 years ago, because of the power of MRI. So that's one piece of it. But then when you go to operate on the brain tumor, what do you got to be careful of? The participating cells, that you don't nick those cells. And that's a key feature. That's a key feature about robotic surgery. And I'll show you what I mean by that in a second. This is a patient who had a very bad tumor, and I can't remember all the details, but anyhow, this was how she looked before surgery. She had brain tumor. She had several brain tumors. And they operated on her. This was in Canada. They operated on her with the NeuroCam Canadian robotic system. And this is what she looked like a year later on the right. So the point, one of the reasons why it's so successful is because they have what they call in these robotic operational systems, I forgot, virtual lines. What are virtual lines? Virtual lines is what the surgeon draws around the tumor such that his implements go for the tumor. And now remember, he's doing the surgery on a screen. The scalpel are all under the control of the robot, but he's moving the scalpel by his fingers on the screen. And on the screen, he draws what's called a virtual line. And where he puts that virtual line, no matter where he moves, no matter how much he jitters, no matter whether he coughs, no matter what, that robot will not move past that virtual line. That is extremely valuable to today's kind of surgeries where you're worried about getting the tumor out without damaging the ancillary cells. Because you damage the ancillary cells, you can kill a patient, you can blind a patient, you can do some very nasty things. So one of the critical limitations of neurosurgery is virtual datum and virtual lines, and how you draw those lines, and the fact that that surgeon can never pass those virtual lines and therefore protect the patient is huge. It's huge. It's huge, and it's getting bigger and bigger and bigger. And it's becoming, I want to say, one of the standards by which when surgeons look at how do we perform this operation, it becomes one of the issues. Do you draw it? Now this happens to be, if I get this right, this happens to be a tumor. And you got to be careful when the surgeon operates on this tumor that he doesn't go too far to the left or too far to the right. So he draws a datum plane around that tumor. And no matter what he does with that scalpel, he will never move past that datum plane. And that's true when he's doing another tumor around the central cord of the brain, or when he's doing heart surgery. And in some cases, the first application of this, the Canadian system, was in Calgary. University of Calgary and Northwest Territories were teamed together. They had a patient that was 4 days old, had a 1/4 inch gap in his heart. And they didn't have enough time to get that surgeon from Calgary to there, but the machine was there in Northwest Territories, somewhere in Northwest Territories. The surgeon did the operation in Calgary and sewed up that 1/4 inch gap in that patient's heart. That patient lived. So the power of this sort of thing is what you kids are all about. It's not just what we do today. It's not just what the astronomy discoveries bring us or what the Earth resources stuff, but it's about the future. It's about what new frontiers it's opening up to make all our lives better and all our grandchildren's lives better. We have these damn technologies coming out every right and left, but we don't have the wherewithal, we don't have the entrepreneurship to deal with them. And what I'm trying to do is inspire you kids to deal with that entrepreneurship. So here comes Mersey. About 4 years ago, he builds an instrument, 5 years ago, called TEERS for Landsat 7, right? 4 or 5 years ago? Right. Using one kind of technology. Today, that technology's been surpassed because he's developed and worked with a new set of detectors called SLSs, strain layer superlattice detectors. 100 times, 10 times more powerful. 10 times more powerful than the Landsat detector, TEERS detector, that's flying on orbit today. But no one, guess what? No one wants to fly. Why? Well, because it's new, it's different. Oh, we can't take the chance. All these typical arguments, right? But we have a way out, don't we? We have a way out. Let's take the damn instrument, let's make a telescope out of it, and let's fly it on station. And let's get it there. And so that's one way we're thinking out of the box. That's one way we're pressing the system. So we hope in 18 months to have his instrument in orbit, the detector, with a little telescope behind it, to do very mundane things. Look at the Earth whenever the station's looking at the Earth. We're not pointing it, we're not doing anything else, because we don't have the money for it. But we do have the patience, the time, and the effort to get it ready and fly it. And what did he do? He went to get it. He went and put the pieces together without any money at all. He just did it on the fly. He put a little teeny cooler, cryo cooler that you could hold on your hand. There it is back there. He put it all together just on his fly. And then all of a sudden, some nut comes along and says, we need to fly that thing. Right? Right. And did he say, oh, no, I can't do it, it's too complicated? No. Not yet, right. Yeah, right, we'll wait for that. All right, so, all right, I got to move on here. But we're talking about medicine, right? We're talking about you, your children, your grandchildren, the future. What are we doing medically today? Well, here's something. This is a camera. This is a 0.5 megapixel camera, and we're buying now 1 megapixel cameras to fly into space to help us with robotic servicing. And that's tremendous. But you know, these cameras weren't made for us. These cameras are made for proctoscopes. And now the company comes along that we're buying these cameras for, because we're building some tools for them for our servicing missions. They come along, and what do they give us? They show us, not give us, they show us a new kind of proctoscope that goes right through your windpipe, goes into your stomach, goes through your esophagus, and allows you and stitches the gap between the esophagus and the stomach lining so as to avoid acid reflux. Patients with very serious acid reflux can take advantage. This requires very teeny cameras. There's two of them on this, so you get stereo views, and it involves some kind of staple machine, which I don't know how it exists. But the point I'm trying to make is there's an opportunity here. This is a 1 megapixel camera. It's about approximately 4 millimeters in diameter. This particular one is only 1.2, but it's only a quarter of the megapixels. But the point is there's technology out there that can do some of the scientific items, do some of the scientific discoveries that you may be interested in. And I thought it was important to show you that the future's not over, the future's just beginning if we think about it in terms of an entrepreneurial sense. What is someone else doing for practical applications on the ground, and how can I use what they're doing to advance my scientific objectives? That's my point. Everybody says, well, what the hell are you talking about? You're supposed to be in servicing, right? I can tell that. So let's talk about servicing. What have we done with servicing? What have we done through the years? Well, first of all, robotic servicing is the only chance we got for the next 10 years because there is no shuttle anymore. There's no human space flight capability in low Earth orbit. Most of the systems we build are for low Earth orbit. Most of them today are A-train kind of systems, sun-sink, which is hard to get to. So what have we been doing? Well, first and foremost, we have put together, and you ought to walk through and see it over in Building 150, a new concept, robotic concept of operations facility. And this is a snapshot of it, but it's not doing any justice until you go over and see it. But we are studying, yes, refueling of Landsat 7, refueling of Terra. And part of the refueling operation is the necessity to have to capture the animals first. These satellites don't always stay in position. Sometimes they lose their fuel, they'll drift out of orbit, they'll wobble, they'll spin, so on. So we have all these different kinds of things. I'll just dance through. First problem is the issue of finding the satellite. So we have and developed here, through some of you folks that I see here, a thing called Raven. Raven is a flash LiDAR system that incorporates both a flash LiDAR to illuminate the subject when the object that you're trying to track down when it's in the dark, a visible sensor and an infrared sensor, and a filter system. And along with it is a computer. But Raven is flying on station in the next 6 months. We hope we can get it to orbit, but it's ready. It's going through thermal vac at Langley, and it should be ready to fly. So that's one of the key issues, one of the key developments for robotic servicing, is the ability to find your object, the ability to process the information that this device puts out, information in terms of tip, roll, yaw, rates, and be able to feed that information to a robot that's 40 inches away, is to about reach forward and grab it. You'll see another view on that. The computer that does the processing got started here in the last year or so of the 4th servicing mission of Hubble, called a Spacecube computer. Very, very fast machine, specializes in FPGA images, processes in microseconds, computes the information, sends it forward to the robot, tells the robot where to go to grab the spacecraft. Spacecube, here, a Goddard design, a Goddard technology. And I think there's something like 6 or 10 of them in orbit already. The robotic arm, okay? A 11-foot robotic arm just got delivered. It's there in the concept of operations facility. Fully robotic. Only thing it hasn't have is environmental test program. We're going to put it through its paces first, and then we're going to try to buy 6 more for the restore mission, for a robotic restore mission that has a capability of doing multiple different functions. Yeah, Jennifer, including putting a new instrument on Hubble. Awesome. I haven't forgotten that. Okay. And we don't let John forget either. Okay. So it's here. Go into 150, see it. Okay, I talked about the robot. I talked about being able to capture satellites that are tumbling. We have the sensor, flash LiDAR, infrared, which we call it sensor. We call VNS. It's also called for station, it's called Raven. But it's sensing what that satellite is doing. It's attached to the arm on a spacecraft base. It senses what that system is doing, computes the correction algorithms for positioning the robot on target, and then the arm moves forward in the last 40 inches and grabs anywhere it wants along the interstage adapter. Most spacecrafts today have interstage adapters that are left on. Hubble has an adapter that we put on. It's even better. But my point is we're trying to do legacy systems that are already up there that may need fuel like Terra, Aqua, or Aura, or Landsat 7, and use those and focus on those systems to develop a legacy capability of taking care of systems that have already been designed and developed. Will we build them that way in the future? No, but it'll take 2 generations to change the thought process of future animals here on this planet. You know, we do one thing one way, we just want to do it again and again and again. Now, this happens to be the full-scale mock-up of Landsat in the clean room, and those in the, in the concept of operations facility. And these are the valves that we have to reach in to refuel the system with hydrazine and helium. And the activity we're going through now is developing those tools that will do that. We've actually done it once or twice or 3 times on orbit, on station, with a similar panel. We've actually done it. We've actually transferred hydrazine equivalent density fuel back and forth to the tune of gallons. But the point is, we didn't say no, it couldn't be done, which was everybody was thinking. All these valves are wired on the ground, safety wired and protected. So the point is that if a human did it on the ground, we think we can train a robot and develop the end effectors for a robot to do it in orbit. So it's all done. I was only going 5 minutes over, right? Yeah, right. Buy everybody lunch. Okay, so I just want to wrap it up and just say this is what it's all about. You folks, your children, and your future generations are really, really what it's all about. Not just this, but it's really advancing the technology across the entire wavefront so that it benefits future generations in terms of economics, in terms of health, in terms of stability, in terms of computation and telephones and you name it. But it's there. It's there. It's representative of the stuff we've tended to do for the most part in satellite servicing, and it represents technologies that we brought with us all the way along for the last 30, 40 years, recognizing that we're going to need these kinds of things in the future. So I'm open for questions. No questions. Lunch. Time for lunch. Thank you very much.